Welcome everyone, and thank you so much for bearing with us. I guess I'm giving the last technical talk, so happy to see so many of you stay around. Basically, what it says on my t-shirt, Antmicro loves open source, is not just a marketing slogan. We're an open source company developing different kinds of services, supporting different kinds of tools and IPs in the open source hardware domain. I mean, we do software and hardware, but hardware specifically in RISC-V, which we've been a founding member, has been especially interesting as there's quite a lot of stuff that still needs to be done. And there is a lot of excitement with building all the new things that need to be built. So I guess we found a really good place to do what we're doing. And specifically, the tools are of very much interest to us because tools enable collaboration. Tools enable people to replicate results. And we happen to be developing quite a lot of different tools for various stages of different flows, both for design and verification. What's important to understand about us is that we're a software-driven company doing hardware stuff. So our primary concerns is how do you kind of scale it all up? How do you make it all collaborative and CA-driven? That's what's on our minds all the time. And some of our customers include, Google, Western Digital, Microsoft, Microchip, and Sci5. CHIPS Alliance, which we're one of the kind of leading members of, is actually sharing a lot of that mindset. CHIPS Alliance is trying to prove that open source silicon is not just about cores, obviously. I mean, RISC-V is a super important part of this ecosystem and the key driver for what we've achieved so far. But that's not the end of the game, right? There's Anchor components that have to go into SoCs, and there are the flows and the tools that go into putting it all together and making it into an SoC. So CHIPS, of course, coordinates very closely to RISC-V, as we're obviously working together a lot, and most of our concern really is RISC-V. Most of the people that want to do open source hardware of any kind is doing RISC-V most likely. So this is our primary ecosystem. And CHIPS Alliance, which I also represent as a marketing chair of, believes that open source is not just possible, but necessary in the tooling space. Because we want to have this unconstrained collaboration. It shouldn't just be just for people that have access to the proprietary tools. It has to be really possible to get started quickly. And of course, at some point, you will have to figure out some very complicated things if you want to make silicon. But it doesn't mean you should have to pay $10 million, on day one. CHIPS Alliance, in this vein, of course, wants to host tooling projects of various kinds. And in fact, we've been very successful in kind of gathering a lot of interesting people under our banner. First of all, of course, the Open Road / Open Lane, Open FASOC, all those open source ASIC design flows. Obviously still a lot of work to do there, and obviously a lot of time that'll pass if we want to really do everything with them. But nonetheless, it's an incredible development. There are real production-grade designs that have been made with Open Road. We have 12 nanometer silicon made of Open Road that's working and performing what it's supposed to do. So generally speaking, it's a very exciting part of CHIPS Alliance. But of course, there's still a long, long road ahead. And I won't be talking about that part today. Then we're also home to the F4PGA toolchain, previously called SymBiFlow. We're also doing a large part of the effort there. So this is to enable open source FPGA development. And this is kind of a nice showcase of how ASIC design could perhaps evolve as well. The way we're now shaping the F4PGA effort is by having an open source interchange format that allows different vendors to have tools that interoperate between open source tools, closed source tools. The important part is we have good delineation between the different parts of the flow and nice standardized interfaces and formats and tools for those formats to allow this. So we believe this is important because FPGAs are an entry point for a lot of engineers into ASICs. They're, of course, the prototyping platform for a lot of ASICs and so on. So we think FPGAs are kind of part of the big ASIC family. Chisel is also part of CHIPS Alliance. We have a whole Chisel work group. I mean, Chisel and Rocket and all the things related to Chisel have kind of landed in our organization. And of course, more broadly speaking, we're thinking of actually renaming this working group that's called Chisel Working Group into a HDL working group because we have quite a few tools related to HDLs that are not necessarily Chisel. And even Chisel itself right now has Vhdl and efforts that kind of want to bridge different programming languages in the HDL space to work together. And of course, that's what I will be talking about today. CHIPS Alliance is home to our open source verification efforts. So it's home to RISC-V as well as the work in Verilator that we're performing. So why do we need open source UVM and SystemVerilog support? You'll have some people saying, well, perhaps that's not necessary, let's skip this. But we believe we really need to bridge different environments, different methodologies to make all of this happen. So we have a lot of great new approaches to verification, to design that RISC-V is spawning, including Chisel. But not everyone will go and adopt those new tools. There's companies with large pre-existing bodies of work who just need some kind of open source alternative and some kind of open source tool to support what they already have, not to have to redesign everything from scratch. And a sustainable result that we want to achieve requires us to combine new and old approaches. So we want to make it easy to just remix stuff together and like use a bit of this and a bit of that and have different design teams collaborate together. We have made important progress here, and we're trying to figure out how to apply this progress into real practical use cases. But of course, there still remains a lot of work that we have to do. So what would this enable? Obviously, we could combine open source and proprietary tools. And those ecosystems that very often people say, oh, these are like two different parts of the ecosystem. We don't believe that really. I think that a lot of people, personally working in those big companies might have a little bit of a different mindset than perhaps their company formally represents, and so on and so on. It's really more of a gradient, I would say, than a clear delineation between here are the hobbyist users and here are the professionals. There's a lot of people that kind of wear many hats as well. So we believe that we have to try to kind of bring them all together. And especially we want to have the chip making companies, the people that are already making chips today, to start benefiting from open source piece by piece, right? We want them to be able to adopt the stuff we're doing without throwing away everything that they already have. And we believe that this kind of lack of licensing constraints that open source has would enable us to do much more scalable and reproducible stuff. Reproducible not in the sense that you can't make reproducible things with proprietary tools, but reproducible in the sense that many other people can recreate your research results and so on. And of course, there's a lot of implementations that are written already in SystemVerilog. So, I mean, if we support them and their test benches, then we're going to have pretty nice results. So we want to build this collaborative ecosystem. We want to prove that open source in the ASIC design space really is possible. And verification is the frontier that we've kind of opened. How do we get there? We took this kind of approach where we first tried to identify what we're missing. We're also trying to reuse as much as we can. There's a lot of great stuff being done in the open source domain. Very often people talk, oh yeah, like there's a bunch of hobbyists that are kind of doing some crazy things. There's a lot of skilled and talented people in this ecosystem building tools that you wouldn't believe the quality of. And by looking at this space carefully, by talking to these people, by integrating those efforts together, a lot of work can be avoided. You don't have to develop everything from scratch. We also want to make it all transparent and well documented, so we have automated tests, we have status reporting and so on. And of course we need collaboration. So part of this talk is also to kind of put it out there for other people to collaborate in this effort, perhaps join CHIPS Alliance, perhaps not. But generally speaking, we want to see who has what and how can we make it work for everyone. And especially important for us is to provide incremental value. It's not just like, okay, we try to boil the ocean and do everything at the same time. We try to get to a practical result as soon as we can and then work from there. So what is missing? First of all, of course, we had to build a test suite, right? We wanted to see how many parts of the LRM for SystemVerilog we support, because we need SystemVerilog for UVM. So we created this SV test suite. It's available on our GitHub, and there's a nice dashboard where we're measuring a lot of open source tools against each other, seeing, okay, which one supports what. And that's been going on for a long time, right? The SV test suite has been developed some years ago already. And of course, we have a lot of test cases, we have test benches, we have different cores being tested, and altogether this constitutes a pretty sizable body of tests that we can kind of use to gauge who's where. And of course, as a result of this effort, support for SystemVerilog in various open source tools has improved dramatically over the years. The second thing, and that's the main topic of today, was okay, to actually do UVM, you need an event-driven simulator. The problem is, of course, there wasn't any open source solution, like meaningful open source solution available. We thought that Verilator is a good choice. Verilator is very well renowned. It's being used for a lot of different things, not verification so much, but still it's kind of very well known and respected. It's very fast. People always say that it's a great tool. Nobody complains about Verilator. The only thing they complain about is that perhaps they cannot do verification with Verilator. So that's what we're trying to fix. So in order to enable things that Verilator was missing, which is time awareness and event support, we actually needed to completely re-implement the way Verilator handles scheduling. So what we needed to implement was a Stratify scheduler of SystemVerilog UVM, and basically there are statements in SystemVerilog which will fall into different regions of this entire flow, and sadly, of course, it's not really fully linear, right? As the arrows show, there's a lot of kind of capabilities to move around this flow, which do require some kind of scheduling. Basically, we needed to implement this in some form. And of course, you can go forward in that flow or backwards. You have to delay some events to later in time. So it becomes a little bit complicated, but overall, it's possible. And we introduced what's called dynamic scheduling into Verilator. So before, it only had the possibility to statically order things at compile time. If you know how Verilator works, you kind of compile your thing into a C++ code that you execute. So now we have the ability to actually dynamically schedule things during execution. And yeah, as the slide says, many of these things cannot be predicted during compilation, because if we could predict everything, what's going to happen, then obviously you'd just do it all statically, but sadly that's impossible. We had to introduce dynamic capabilities. And our approach has been to use coroutines. So we've had several approaches, right? This was not created in one sitting. It was actually a pretty long body of work. And our first implementation actually used threads, because we thought, well, we only need a prototype of this. Let's see if we can use threads to do this. Sadly, of course, the performance that we got from that was pretty horrible. And Verilator is supposed to be a fast simulator, so kind of decreasing the performance by several hundred times doesn't really count, right? But we did get it to work. That's the important thing. The thread-based POC was really important because it showed that, okay, this is possible. You can do this. Then we sat and thought, okay, how can we improve this? And it turns out that C++ as a language, which is used to develop Verilator, has been developing itself, right? And the notion of coroutines, which is of course well known for many years, was introduced into C++20 as a first-class language construct. So we could just use that to implement very lightweight, simple threads, or like thread-like stuff, that would enable us to schedule those tasks. And it turns out the overhead we're getting is, well, no more, let's say, right? So kind of the overhead that we're getting over regular Verilator is kind of negligible. So we kind of we degraded by several hundred times, and then we improved by several hundred times in the process. So overall, it's been a few passes to get there, but we managed to get really, really good results. And you can read about more details of this in our blog note. We have a whole blog note detailing how it's implemented. It's actually fun because coroutines are quite cool. So what can you do with this? First of all, you can do delays, you can have event variables, you do the fork and join statements that you need, you can do waiting, so everything related to just scheduling. And then we also, of course, moved on to add more constructs that are needed for UVM. And we started with constraint randomization. We've managed to do some progress there so far. But of course, to really do full UVM, we'll have to implement a real solver, which is some not insignificant amount of work. But the work has started, so I'm optimistic. If you want to try what's already been achieved, the dynamic scheduler has examples. So we compiled the right version of Verilator, and we have some examples that you can run. and you can play around and see what's possible and perhaps try to break it and see what's not supported. There's a whole CI, and you can just take a look at how it's built, and you know, that'll explain everything. The other track of our work has been improving the general SystemVerilog support inside Verilator. Well, not only Verilator, we're also improving SystemVerilog support in Yosis and other places, Open Road. And the reason for this is, of course, that when writing UVM code, you'll probably use some SystemVerilog constructs which probably weren't yet supported in Verilator. And for this, we're using what's called the Universal Hardware Data Model, UHDM, which is a framework for kind of plugging parsers and various kind of other tools into things like, well, Yosis and Verilator. So UHDM allows us to reuse the same code for different frameworks. So it's the same kind of library, except it's being integrated into different frameworks, and that kind of saves a lot of time because we don't have to like rewrite everything from scratch every time. Of course, it took some effort to actually integrate those libraries into both Yosis and Verilator. With Yosis, we have a very good setup because we actually have a plugin-based infrastructure. So you can take vanilla Yosis from the internet, and you can grab our plugin, and it should work, right? And then for Verilator, there's still some work to integrate it properly, but again, that's just work. So anyway, already in late 2020, in this part of the work, this is more like Google-sponsored work, we could already parse and synthesize and simulate IVEX, as an example, back in late 2020. So this is not new. And that's a really rough diagram. It kind of says, yeah, we're using libuhdm on both sides of the equation. So all of this is actually leading up to a pretty cool announcement because Verilator 5 will actually be containing our work. Not only, of course, there's a lot of new and exciting things coming into Verilator, but Verilator 5 will already be able to do event-driven simulations. You'll be able to run your test benches in SystemVerilog, so you won't have to rewrite your test benches to C++ to get them to run in Verilator. You'll only have to write the main function, which is like trivial. So that's already, I think, a nice and you know, kind of little improvement that people will be able to experience. So this kind of stratified / dynamic scheduling will be integrated into Verilator soon. It's going to be released as version 5. And there's also other cool stuff that are useful for this effort, such as kind of some changes regarding the static scheduler that bring it closer to what SystemVerilog LRM kind of expects it to be. So overall, kind of, we're not the only party doing this work. We're doing much of this work, but there's other people contributing too, and altogether, this is kind of lining up really neatly. So what else remains to be done? Of course, as always, the list is long. It's not that we're done, but it's also a finite list, right? We need to implement things like clocking blocks, assertions, class parameters, cyclic randomization, unpack structs, and functional coverage to get to UVM proper. We will, of course, have to kind of optimize things to make sure that it works, and we will have to take the UVM work that we're doing and fully integrate that into Verilator. So there's kind of plenty of stuff in front of us, but again, we're trying to identify where we can really already now apply this, what we have today. We're looking at, for example, verification test suites like RISC-V to see, okay, which of these elements are necessary to make it work. And our goals are to, well, obviously enable full UVM in Verilator, and but we're approaching it from a practical perspective. So we're looking at real-life production-grade designs from our customers, and we're trying to gauge, okay, so how far away are we from running them in production? And if you have designs that you think, you know, might be suitable and you really think you could benefit from this kind of open source UVM, you should talk to us and we can kind of get you a study of, okay, how difficult will it be to support you? And of course, the more of efforts we can pull into this, the more money we can put on this task, the faster we'll get there, right? It's not really that far away, we think. But of course, it all depends on our throughput. And one obvious target, of course, is always just the open source stuff you can find. And we're going to do that. But I think the most interesting challenges are presented by actual production designs that people have. So we'd be very happy to hear from you. And also, as a consequence of this effort, I think that this will also lead to open sourcing more test benches, because of course, as we complete the flow, more people will be tempted to actually open source their test IP, because they'll figure out, okay, now this is actually useful. Open sourcing something that cannot be run using open source tools it's a good thing to do, but of course it's not as powerful as open sourcing something that actually runs in Verilator. From other news that we're kind of announcing here, we're looking at Vhdl support, and we have some interest in, obviously in Europe, Vhdl is being used quite a bit. There are certain areas of industry that use it, so we think we can actually get it done using UHDM. We've been evaluating the effort involved, and it's not tremendous, but it is some effort, of course. So yeah, we're also looking for interested parties, because Vhdl wasn't traditionally our focus. We're mostly using Verilog, SystemVerilog with our customers, but it doesn't mean that we don't have to enable it to make everything work. So we want to look at what kind of mixed UVM test benches can we implement, how quickly, and we're also looking at some event-driven use cases that aren't necessarily full UVM, but people just didn't even know that they were possible with Verilator, and that involves Vhdl, so we need to do this. Last but not least, Intel, who's been presenting just a second ago, who's also a CHIPS Alliance member, came up to us and wants to contribute their System C compiler into CHIPS Alliance, which is great, because we want to support as many HDLs as we can. And this tool actually generates SystemVerilog. So basically our working concept is just go through the regular flow and it should work. And also there's this concept, perhaps we should go from the System C compiler into UHDM. That's another way. Might be more like elegant to do that, but we also think that, well, let's leave elegance for later. We'll kind of do the two-step flow and it's probably just going to work. But this is kind of a really new development. But also let us know if you're interested. If you're using System C stuff in your test benches and you think that would be useful for you, then of course, like, it's all a matter of prioritization. So that's it for me. Thank you very much.